Thanks, Joe. Thanks, first of all, thanks for the organizer of Linear Connect for inviting me. This is really an honor for me to be able to speak to you about big data and big challenges for ESA. So I realize I'm going to speak in front of an audience which is quite different to the one I usually speak in front of, and also in front of many technical experts. So I hope you bear with me, and I hope that still you will find my presentation inspiring. So I'm going to speak about big data. I'm going to show you some nice pictures as well. I'm going to speak about space data management, how big data is bringing new big challenges for ESA and other space science agency. And also I'm going to show you some cool tool that you will be able to use, because everything is accessible on the internet. So I'm the head of the Data and Engineering Division at ESA, and I'm in charge of all the ESA space science archives. And I'll describe that a bit further. I'm based in Madrid, and I'm French. So first, some nice picture. These are some pictures from the Hubble Space Telescope, which was launched in 1990, which is still operational. So you can see really stunning images in what we call in the visible. So you can see some galaxy here, the Wheel galaxy, conjunction of two different galaxies on the right side, and also a magnificent cloud on the left side. We also launched some years ago a spacecraft called Planck, and the idea of Planck was to look at the Big Bang and to understand how the universe had been created. So by measuring the light which was emitted billions of years ago, then we were able to build this superb map. Also, the idea, we are launching different type of spacecraft, and the idea is to look through different wavelengths. So you can see here various pictures taken from different spacecraft, Herschel, ISO, XM Newton, or Hubble, and you can see that depending with which eye you're looking at the sky, you can see different things. Obviously, when you look from the Earth, you usually can see these kind of things, but when you look with Hubble, then you can go outside the atmosphere and you can see much more details of the images of the sky. Then if you look in the far infrared, you can actually see the same picture here. You can see this, what we call the pillar of the creation, but you can see how further galaxies or further stars can be shown behind the scene. This is Gaia. So Gaia was launched recently, and this is one project. So we are counting the stars with Gaia. We are going to count, we are more than 1 billion stars. We are making this huge catalog, and this is one of the projects which is actually bringing us new challenges compared to the data that we used to have to deal with. So I'll come back to that specific project later on, and I'll show you how we are doing data management with Gaia. Also, SOHO, this is a spacecraft which is actually looking at the sun. So you can see the sun is too bright, so we are hiding the center of the sun, and we are measuring this, what we call coronal mass ejections. So when there are big bursts of the big explosions on the sun, and to understand what are the effects of these ejections through the magnetosphere and up to the Earth. And in some cases, this can also have impact on some of all the devices that you are also dealing with. And these are these phenomena which is actually creating the aurora around the North Poles. So all these data are available online, so you can easily access them, access to them. We are also going to Mars, so we have two spacecraft now orbiting around Mars, one called Mars Express, another one called TGO. And the idea is to look for ice, because we consider that ice would be the possibility of life on other planets. So that's what we are doing. So you can see different type of images with a high-resolution stereo camera on board of Mars Express. So there is this other project which you might have heard, which made the news a couple of, a year, 2 years ago, about Rosetta. This is quite an exciting project. So this was about launching a spacecraft to encounter a comet and to land on the comet. So this is, imagine you're sending a spacecraft to meet a comet which is 500 million kilometers away from the Earth. So it took like 10 years. between the launch date in 2004 on the rendezvous with the comet in 2014. And then this comet has had this funny duck shape. And this is the little selfie taken by the spacecraft. And then we tried to land on the comet, sending this little lander, which is called the Philae, that you might have heard about. It's quite a challenge. So in fact, didn't really land properly. He bounced 3 times. So we said we were very proud to say that we didn't even land once on the comet, but 3 times on the comet. Okay, so ESA, I think ESA is a bit like also the purpose of this conference. This is a lot about collaboration. So the idea is to put together 22 European member states, well, mainly European. There is some collaborative states with Canada, to work together on space project, only for peaceful purposes only. So there are 8 sites, facilities all across Europe, so with about 2,300 staff. And I am based in the Spanish center, close to Madrid. Over the last 50 years of ESA, we've launched over 80 satellites, and many of them are still operated. In fact, this morning we launched one. We launched Sentinel-2B, that you will probably hear in the news, so which is an Earth observation spacecraft to monitor the climate change. So lots of collaboration amongst all the countries in Europe. So the idea is that is to collaborate together, because it's quite difficult for individual countries to do some big space projects, in particular the ones that I've shown you, like Rosetta or Gaia, that I will speak a bit more about. I mean, that would cost too much for one single country to do it on its own. So the idea is to unite all the forces, European forces, and to build a spacecraft together. And they are continuously, so it doesn't depend on the European Commission. It was created many years ago, as I've seen. So the member states are almost the same, but not exactly. So that's for historical reasons. But we are having very close collaboration with the European Commission. In fact, the spacecraft sent this morning, Sentinel-2B, is a collaborative agreement between ESA and the European Commission. So we are doing many activities. So like Earth observations, human space flights, we are participating to these international space stations, we are doing launchers, navigations, operations, technology, telecommunications. But the main thing where I'm working in the space science, and this is what I'm going to speak about. So what you see here is just one activities of ESA. There are many others. So for example, Earth observation, the one that was sent this morning, the Sentinel-2B is more in the Earth observation domain. So these are the fleet of all the spacecraft that we have launched, which are look in the solar system. So between here and the sun, and studying various planets. So many of them the first one have been launched in the early 90s. And many of them are still being active. Some of them are not working anymore, but you've seen SOHO that I've mentioned today, which is still active. Venus Express, Cluster, Mars Express, Rosetta. Rosetta now is not active anymore. We actually, after landing on the comet, between quotes, now we did, some people wanted to call it, we crashed on purpose, we crashed the spacecraft on the comet. People from the operations center, they said they made a controlled impact on the comet. And why did we do that? Because there was no more solar energy, not enough solar energy due to the trajectory of the spacecraft. We would not have any more energies to continue to use the spacecraft. So what we did is we did this controlled impact on the comet, which enabled us to take images on the comet up to 50 meters. Before actually impacting the comet. So this was quite impressive images. Then outside the solar system, we are also, we've sent many spacecraft. There are many operational as well. So you can see here the different wavelengths from the microwaves to the gamma rays. And the idea is that we want to look at the sky with different eyes, as I've said before. And I'll show you some images, how the sky can also look very different from one image to another, from one wavelength to another. So it's a mixture of spacecraft which are not working anymore, and some of them which are still in operations, like Gaia, for example, like XMM Newton, like Integral, and also some which we are now developing. And this will bring some challenge also, because we need to keep this data forever. So we have this concept, and I'll come back to that because we consider this is really a treasure for science, maybe for humanity as well, but really for science. So we need to keep this data available forever. So that's one of the challenges of the archives we are dealing with. So indeed, at ESAC, so the European Space Astronomy Center, we've built a science data center. So we like to call us the digital universe of the digital library of the universe, maybe the European digital library of the universe, because obviously there are many other digital libraries of space science worldwide. But in Europe, this is the place where we have all the data from the space science, ESA space science missions. So today we have archives for about 15 missions, so as I said, covering astronomy, planetary and solar system missions. And we have these archives for all, some of them are static because we don't get new data. Some of them we get new data every day, and some of them are being prepared, so when the satellite will be launched, the archive will be immediately available. All available online, as I've said, I'll come back to that. And we have different types of users. So our main users are mainly targeted toward professional scientists, so professional astronomers or professional planetary scientists. But it's true that we see some amateur astronomers who are also coming to our archives, and I'll show you a couple of tools where you can actually use yourself. And it was interesting that SOHO, the one you saw, the two little videos with the sun on these bright filaments. So this is being used by amateur astronomers to actually discover comets. So they are going into the data and they are discovering comets, and they've discovered more than 10,000 comets. So this is something we didn't plan to do, or we didn't have the money to do, but the community amateur astronomers are actually doing. So we mainly serve the scientific community with public access to all the data. I'll come back to that. And also we serve the people who are the teams in Europe who are actually building the instruments on board the spacecraft. So we have three main challenges, three main objectives for the archives. The first one is to maximize the science exploitation of this data. So obviously, this is a really scientific treasure for science, and we want to make sure that we can provide easy access on tools which scientists can actually do their science with. So this is really our main focus. Then we need to keep that forever. And forever is difficult. I mean, you know even better than me that technology is changing. The IT technology is really changing radically very fast. But we still have to keep data from 20 years ago. And I'll show you which technology we are using 20 years ago and then how they have evolved over time. And the third one is more an internal process. So we are actually supporting what we call the operations team, the people who are working on the spacecraft. So this is more an internal one. So the two ones are more, let's say, towards the external community. So you can see here a snapshot of the web page with all the spacecraft archives. So at ESA, we have an open data policy. So it is usually open after 1 year. We have this concept of 1 year proprietary period. So the idea is that usually the ESA finances the spacecraft, and the instruments on board the spacecraft are actually built by national funding. So the teams who are being funded by national funds, they usually have proprietary access to the data for a year, and after a year, then the data goes into the public domain. Then it is fully accessible worldwide. I mean, you can access it very easily. It can be copied, it can be reused, it can be analyzed. I mean, obviously, most of the people, most of the scientists use the data to analyze it further and then write scientific papers, or they write their PhDs, or they write paper in the literature. But as I said, it can be copied, or it can be reused by other people, and we have cases where the data is being copied on other sites as well. Everything is available through the internet, through standard web browser. That looks quite obvious today, but remember we started in the 90s. So in the 90s, the internet panorama was not the same as it is today, so that was not necessarily obvious in the mid-90s when we started. In fact, in the early days, the archives were on CD-ROMs. We had to ship the CD-ROMs to the people. Obviously, today we do everything on the internet. And it really works like, as I said, the archive is working like iTunes. You know, you search for the information that you're interested in. You can have preview of the images, then you select, and then you download. The big difference with iTunes is that you don't need to give your credit card number. So we are not the only one, and I think it's interesting to see here in this community, this, I mean, I think the name carries it very, very nicely, Linear Connect, this community worldwide working together. And obviously ESA, even if we are collaborating within Europe, we are not the only one faced with these challenges. So we have, 15 years ago, we created the so-called virtual observatory, VO. I know that in the IT world, VO sometimes is for virtual organization. So VO in our case is virtual observatory. Sometimes I call it VOps or VO. So in my presentation, VO is like virtual observatory. So we created an alliance with around 20 members all around the world, with the US, with Japan, most of the countries in Europe, with China, with Chile. When we are working together about interoperability. And I think that's something that you're also doing here. So we are working together to ensure that we can interoperate all our archives together because the scientists, they don't care where the data comes from. They don't care if the data has been taken by NASA. They don't care if the data has been taken by a ground-based telescope or by a spacecraft from ESA. They just want to have access to the data. Science has no frontier, as we say quite often. So we have created this VO, and then the idea, as you see this is very top-level architecture, where we have all the resources with the spacecraft, the ground-based telescopes, data computation, or a simulation, and at the top, we have the users. And in the middle, we have to find the data, to get the data, to share the data, and then to use the data. And what we've done basically is that the VO, Virtual Observatory, is the technical framework which enables these connections between the resources on the layers, the user layer. So I'll mention that because it's something that has been revolutionized quite a lot, and you will see that in the rest of my presentation. So this is why this is coming now. So we created a lot of interoperability standards altogether, and it's quite difficult when you work, even if this is really a scientific environment, so where there is no economical or financial competition. When you have to agree with 20 projects all over the world about interoperability protocols, this is quite a challenge. But when you make it, then you will be able to offer a framework to the scientific community that anybody can use, seamlessly accessing data from one place or another. So these are the various aspects that we've created some standards about format of the data, about data models, about query languages, about semantics, about also how to access computations or data collections, and also some at the user level and the application level. So we created some protocols which enables various applications to speak to each other, because there is no one killer astronomical application. So usually there are a set of applications which can do different things, and then the idea is to delegate to another application where the application is most suited to do your work. If you have to look at spectra, if you have to look at images, you might not use the same tool. But if you find spectra, then you might want to delegate the visualizations to an external tool. So I'm not going to go here into the details, but these are the type of protocols, so you get an idea of the type of protocol we've been creating. So that we have had some yellow pages of all our services. This is what we call a registry. We created some kind of query language, which is like SQL for astronomy, called Astronomical Data Query Language. This SAMP, this Simple Access Messaging Protocol, which enables interconnectivity between applications. Then on the right side, many ways to access the data. So the data are quite different, depending if it's a spectra, if it's an image, if it's a catalog. So we created different access protocols. So simple image access protocol, simple spectra access protocol, table access protocol. Then when you have to do job scheduling, we created this UWS. VOSpace is something which is also now quite relevant in the context of big data, and we'll come back to that. So it's becoming more and more difficult to bring the data, to ship the data from the archive to the user. So we have to provide ways for the user to work where the data is, and VOSpace is an answer to that. Some kind of Dropbox for astronomy. So a bit of architecture. So this is the standard archive, so XMM Newton archive. This was launched in 1999, just before the Y2K bug, if some of you remember. There was this big crisis about the year 2000 bug that all the IT systems were going to go down. So we launched it just in December 1999. People were afraid to be on the first launcher after year 2000. Okay, so so it's been working for the last now 18 years, or 17 years. It's about 10 terabytes of data, so it's not a lot of data. So we have all the data on disk. We extract all the metadata, we put them in the database, and we have a standard browser GUI. So through HTTP, a user can access the browser, and she gets the access to the data. Then the data is being, as I said, the user can download it directly with FTP, and the concept here is usually the data is being shipped up to the user. Now, what we've seen over time is people say, oh, GUI is fine, but when I want to link it with computation, then I'd rather have a command line API so I can access it much faster, and I can do some further analysis rather than with a GUI. Is not the most appropriate to do more intensive computation. Now, the VO came in the mid-2000s, so what we did is we built a VO layer on top of our APIs. So then VO applications could actually use through this VO protocol, so image access, spectra access, or table access. So we built a layer on top of our architecture, because obviously we could not redevelop all our architecture. I mean, typically the development of an archive is several years of effort, so when a new thing is coming, we cannot just change it fully. So we adapted building this VO layer. And as I said before, so also we can have interactions between our GUI and external applications using this simple application messaging protocol. So, as I said before, we have to keep the data forever, and this is quite a challenge for us. We always speak about big data. Usually people speak about big data in the volume context. Sometimes there is one of the V's of the big data is also the heterogeneity of the data. And we have here data for a long time. And you can see when we started to work on the first archive for the ESA Space Observatory, archive was in 1998. So I don't know if you remember what type of technology could even exist in 1998. Then little by little, we build more and more archives with XMM and then all the others. And you can see that the speed at which we are building new archive is getting bigger and bigger as time is passing by. Obviously, we are reusing a lot of the architecture and the technology from one archive to another. Usually I forgot to say, usually every mission has its own archive because it has to serve some usually it has its own data model and it has to serve some very specific purposes. And one of the challenges here is to ensure this long-term preservation. How do I still give access to the ISO data which was taken in 1995? When I started to work, I quite often tell this anecdote. When I arrived at ESAC around that, in Spain at that time, the people from the facility site services, they were already happy. They said, look, we built these special rooms where you can put all the tapes from ISO. And the room was maybe 1/3 of that room. And I said, well, we are not going to use tapes, we are going to use CD-ROMs. And they were really disappointed to build this big room, where at the end we only used maybe 2 CD-ROMs, which was the 2 CD-ROM jukeboxes the size of that table. And today, you know, I could have the ISO archive just in a memory stick. It's only 170 gigabytes. So over time, but this data is still being used, this data is still being accessible, and the complication here is not so much the size, because obviously the size is very little, but if I give you a USB with 170 gigabytes of data, you're going to have a hard time to find it. If I provide you tools, if I've extracted the metadata into a database, if I provide you proper query mechanism, if I provide you easy mechanism to access the data, then I can still provide you a service. Otherwise, just giving the data is not enough. So this is the archive technology evolution over time. So when we started in 1995, we decided, 1997, we decided to use Java. Everybody today is using, Java is a well-established industry standard, but in 1995 it was not. And in fact, so we developed, we considered to build, obviously to build online services. It was not possible really to use HTML on CGI bin script at the time. I mean, JavaScript was not what it is today. So we used Java, which was the only way to actually provide us with the functionalities that were required. But we were using Java 1.1. We had to develop a lot of in-house communications between the client and the server. We used commercial databases, mainly Sybase and Oracle. And then 10 years later, we started to evolve that. So obviously, we replaced our in-house development by Spring. We put this VO layer. We used open source databases, and there were also some specific extensions, for example, for Postgres, some extensions, which pgSphere, which enables us to do some easy query on the sky, so which was a very big for us, very big advantage. Then the Mac OS become more and more used in the scientific community. People also, the support to Java was less good. The web had evolved a lot, and people complained that, yeah, Java, it's a pain, you need to have Java installed, it is not installed on my browser, so I cannot start your archive. So we migrate to web thin client. Now we had a team of 20 people who was Java experts. So what do you do with this team when they still have to maintain all the previous archives? So we did some technology survey, and we are using Google Web Toolkit. Now for new ones, we are using Vaadin. We use HTTPS, continue with open source and visualization tool. Now I'll come back to that. We are at the moment we are rethinking what to do. Now we have to deal with big data. This new concept of bring the code to the data instead of bringing the data to the user. Data mining tools, high availability. So we are looking at new type of databases as well. So, but we still have to provide support to the ones that was created in 1997. Some snapshots of some of the archives as they were created in 1998. So query panel, results, preview, you can select, you move them to your shopping basket, and you can download the information, the data directly. Then the second generation in 2005 with Java Web Stars, which was already more user-friendly because we used lots of Java GUI elements, whereas in the first instance we developed everything ourselves, even the scroll bar, because the scroll bar for Java was not properly working on some browser. And now we are using a web thin client because it's, I mean, much faster to start. You don't need Java installed and so on. Gaia. So Gaia, as I said, is the spacecraft counting the stars with Gaia. So we are counting the stars, or many stars. So the idea is to count between 1 and 2 billion stars. So with a measurement, so we are counting the stars and measuring their exact positions, which is quite complicated. So we are doing this survey of all the sky, which will go over 5 years, and every 2 years we will release a version of what we call the Gaia catalogue, which will be around 1 to 2 billions of sources. But we are doing much more measurements, and this is where, like you can see here, the number of measurements, 10 to the 11, 10 to the 12, 150 million spectra. So this is a lot of data, lots of different events, and very different type of events. All of this needs to be processed. Again here, connectivity, connections between people. So ESA, we cannot do that on our own. So the Gaia data processing and archiving center has been set up. It's working some kind of train. On the data is, the main database is located in Spain, but then there will be processing being done in France, in Italy, in the UK, in Spain as well, in Barcelona, so not in Madrid where we are, but in another place, in other places in Europe. So that shows you the complexity when you have to move data around and do this processing train, what we call processing train, where data needs to be processed one after the other, and then every time going back to them. This could be the purpose of a talk on its own, but I'm not going to dwell too much into that. Just to give you some numbers here, the main database is 216 terabytes. We estimate that by the end of the missions, the database, so not that, will be around 1.4 petabytes with you can see the number of objects which are going to be measured, so 1.3 billion times. We will have 1.3 billion, sorry, 1,300 billion measurements, or 6,000 billion measurements, so that's a lot of measurements. So is this really a big data or not? I mean, sometimes people are asking me, so the volume at the end is going to be 1 petabyte. So 1 petabyte is not so much big data as far as volume is concerned. I mean, even remember that our spacecrafts are, I mean, Gaia is like 1 million kilometers away from the Earth. So on specific points where we can do the survey, specific point in space. Now we need to transfer the data from that spacecraft to Earth, and that limits a lot the bandwidth that the amount of data that we can get. Our friends from the Sentinel-2, which was sent this morning, for example, will probably observe several petabytes every year because it's on a low Earth orbit, so just taking picture at the sun, at the Earth. Ground-based telescopes also can generate various petabytes per year. For us, it's 1 petabyte. So from the volume perspective, it's not going to be so big. Now, obviously, from the complexity of the data processing, this is very complex for us. It's about 10 to the 20th flops. Very different type of data, so source catalog, spectra, transit, thousands of billions of them. So this is where really the big data is eating us. Okay, then the other two, veracity and value. So as I said before, this is a unique project, so we have to make sure that all the measurements are done properly. That's quite challenging as well. And we believe that the measurements of all these 1 billion stars is going to have an accuracy around 10 times better than what has been done so far. Gives you an idea what we have today. So in orange, the big numbers today. So we have two catalogs which are about 1 billion rows, which then forces us to change the way we are dealing with things. If we look over time, I mean, as I said, with ISO at the beginning, so it doesn't even appear on the graph. Now with Gaia, we are going to double, or more than double the data holdings that we are having at ESA. And if we look to the next, so Gaia will have 1 petabyte. And if we look at the next project, which is called Euclid, which will be launched in 2020, it's going to be 150 petabytes. So maybe in 2020, 150 petabytes is not going to be a big challenge. But for us, you can see then basically we'll wipe out all, as far as volume is concerned, all what we used to have before. Now, we are now at this point of time where we have this change of paradigm. So these are exploratory. We know that this is coming. We don't exactly know how the scientists will react. So, but what we feel in particular for the Gaia catalog, the model that we used to have, the iTunes model, let's say, that we used to have, is not going to work for Gaia because the volume of data is too big. So we need powerful query mechanisms. Sometimes when you do query in a catalog, or what we call crossmatch, you want to compare one catalog which has 100 million sources with another Gaia catalog which are 1 billion sources, and you want to tell me how many in these areas of the sky, how many of these sources are the same between the two catalogs. Okay, that doesn't take 1 second. That can take some more time. So now this query mechanism needs to be asynchronous. Now that the VO is being used by all archive services worldwide, instead of building a VO layer on top of our architecture, we decided to put VO inside our architecture. User cannot download all the data. Today they can download several gigabytes of data, maybe 50 gigabytes of data, but I mean now tomorrow 1 petabyte of data. Not every scientist has a desktop with 1 petabyte of data. And even if it has, again, the organization of this 1 petabyte is the complex thing. So one of the messages here is that quite often the problem is not the volume. With 1 petabyte, you could always buy some disk and put everything there, but how to organize that. So what we need is to enable the people to work into the archive. So we are creating this user workspace in the archive. So not only for disk space, but also for database space. So we are going to give some database spaces to the user inside the archive. So they can, if they make a query for this big cross-match, as I've said, then maybe the result is going to be 10 million rows. If it's 10 million rows, I mean, if you want to have a CSV file back on your on your desktop with 10 million, you will probably need another database there to continue to deal with that. So the idea is to give that inside the archive itself. So this 10 million rows table can be stored in our database, so it is indexed, so it's going to be fast and everything. And science is about collaboration, so usually people want to share this information, so share their data and share their databases with other users. So this is this whole concept of bring the user code, and then the other thing is to bring the user code to the data. Once people store their data or their databases inside the archive, then they want to bring their code there and then do some further analysis. So we also need to provide some services which will enable them to actually run their code onto the data. And the next extension, obviously, is that they want to share their code with other people as well. So this is this big paradigm shift, so what we call also sometimes the Archive 2.0 concept. So if we look again at the architecture, if you remember the simple architecture that we used to have for XMM Newton archive, so if we look at the same for Gaia, okay, we still have all the data on disk, we still have all the metadata which has been extracted on the database, put in the database. Obviously, this is much more complex and much more, we need more disks, we need more performant databases, but remain still with PostgreSQL today on PGSphere we managed to. Now, as I said, maybe if you do a query, you won't get a direct result, so we need to put in place a job scheduler mechanism. So if you do a query, if it's going to take more than 30 seconds, then we need to schedule that to a later stage. So we use some VO protocols on the way to actually do job scheduling. In that case is using the universal worker service, and to access we are using the standard VO protocol, so table access protocol on astronomical data language. And we create this user space inside the archive itself, so both users can have disks and can have databases. So what this the model we call VO inside. Then all the interfaces to the archive will be used with this VO protocol called the TAP, Table Access Protocol. So if we have a browser GUI, we'll use TAP as well. And then the data, if really the people want, they can still ship the data to their place, but then sometimes it's taking too much time. So maybe some snapshots here. So this is the SQL access to the database, so very different from what we used to have, where people could actually just input some parameters and get the list of things. In the case of Gaia, they want to query a big catalog, which is 1.1 billion rows, which can have 800 columns, so you don't want an input form with 800 parameters. So we decided to use this SQL, ADQL specific query language as, specifically linked for astronomy. People can also upload their own tables. So you say, yeah, I want to do this cross-match of my 1 million table of objects against this 1.1 billion table of Gaia. So what they can do is they can upload their own table into the archive, index it in their database space, and then they can do the cross-match with the Gaia archive. They could have done that. If they would have wanted to do that at their place, this would basically be impossible. They would have to build their own databases. So in that case, we offer them the service. And once it is in the database on the Gaia archive, then it can be shared by any other user. This is some ideas of when you want to cross-match big catalogs, so depending on what we call the field of view, the radius into which you're doing the cross-match. So usually things, we are trying, even if you cross-match, so 2.5 million, 2.5 million rows to 1.2 billion, then it's going to give a 50 seconds result. So it's still reasonably fast. Now you can store everything in VOSpace, as I've just said. So it's a bit it's like Dropbox. People say, why don't you just use Dropbox? Well, because Dropbox does not support the VO protocol. So if we want our applications to access Dropbox, we can't really do that. So we have this specific VOSpace protocol, which enables to basically access your files and share your files with other people as well. And it's being accessible by various VO astronomical applications. VOSpace, so basically that's the way it works. You go to the archive and you can say, instead of downloading it, you just send it to your VOSpace. The same for the command line API. So again, it's using TAP. So here we support various type of languages, C++, Java, Python. Python today is the one which is being mostly used by the scientific community. Again, this is changing regularly, but over the last 3 or 4 years, Python has really becoming the main language used by scientists. All what you can do with the GUI, you can do with the command line. So you can upload the table, you can do the Crossmatch, you can move things to the VOSpace. So everything that can be done into the GUI can be done with the command line interface. Then, okay, naturally we get for free because we've developed the interface for all the VO applications, so we get it for free. We don't have to develop a new VO layer because we have VO inside. So some examples here. So again, you go to you see your result, and then you can send through this VO protocol, you can send it to a tool which is called TopCat, which enables to visualize tables in various manners and to manipulate that table again. On the result, you can store it back into your VOSpace and again share it with other people. This is where the next thing is coming, is this bring the code to the data. So this is new from the first 3 you saw it already from the XMM cases, but in the case of Gaia, so we created the so-called Gaia value-added interface portal, GAVIP. So this is this new thing which is more proof of concept for the time being. So here is to create, and I use the iTunes comparison previously. The idea here is to create like an app store. So in the GAVIP, people would be able to write their own bit of code and publish it into the GAVIP, into the AVI portal, so then it can run on the data which is on the archive. So either directly on the archive or in the VOSpace of the users. Again, using all these VO protocols such as TAP, for example. And what we are looking here as the technology, I think I've heard it also this morning. I mean, Docker is the technology we are looking at to actually enable these services into the archive. So we have 4 demonstrators which are being developed these days, and that we believe that this is going to be the way that people will be able to do data mining where the archive is. What we don't know yet is how much computing infrastructure we're going to have to give to the user. So this is one of the challenges we've not answered yet. We'll see how much take-up will take place by the community, and then maybe we will, if this is too successful, we will have to put more computing resources. We need to visualize all this big data again, so there are various ways to do it. Creating some visualization snapshots so that people can zoom in. But I'm going to spend a few view graphs on a tool, which is quite a nice tool which is called ESASky, and which enables to visualize big data coming from many missions. Before doing that, we are also exploring these 3D visualizations of all the Gaia data. So imagine you have 1.1 billion stars that have been measured by Gaia. And what you usually see when you look at a constellation from the Earth, you see the constellation in 2D. But here, when you look at it in 3D, you realize it's not flat at all. So it's quite interesting, and we've had some proof of concept also using the Oculus Rift, and also with the handles, which enables you to actually navigate through the galaxies and looking at real Gaia data. This is not just a Star Wars movie. This is real data which have been taken by the spacecraft. Okay, on ESASky is the last point I'm going to speak of. So the idea of ESASky is, as you've seen, we have data from many astronomical archives. And every archive has its own, every mission has its own archive. Now, there are more and more archives, so what we want is to go one step further. And instead of having to go to every single archive, you can go to one tool where you can see the data from all the archives. And this is what we've done with ESASky, which is basically a tool sitting on top of all our archives. And what we wanted to build a tool here, and this is why it can be used by more people than just professional astronomers, something which is project agnostic. So if you go there, if you're an amateur astronomer, then you can probably find your way. I mean, I'm sure you can find your way. You don't need to know anything about XMM, or you don't need to know anything about Herschel or about Hubble. You can just look at the sky, explore, zoom in, zoom out. It's a bit like maybe Google Sky, or maybe, but with real data from all our spacecraft. we are using this technology which is called EPS, which basically splits the sky hierarchically. So you, a bit like, so various tiles. Not sure you can see it very well, but this was just to try to give a zoom in. So you split the sky into various tiles, and then the more you zoom in, you just get the tiles which are in your field of view. So you can see it here. This is the full sky. We don't see because there is too much light. But then as you zoom in, you go and see more and more details. And this is very fast, in fact. So once you're in your field of view, you can see in different. You can see all what has been seen by all the archives from the missions. And if you click on that, you will actually get to the real data. So you will get a table with all the data, and you can visualize the data, and you can really download the data. So this is not just, it can be used just to visualize the sky, but you can also use it to actually download data from various missions. And in a few clicks, you can download data of half a dozen missions very easily. So you can try it. If you all try it at the same time, so sky.esa.int, okay, maybe it's not going to be that fast, but the network of the hotel is the linear network is going quite fast. So the idea here is that you can look at the sky with different eyes, as we said before. So you can see it with in the X-ray, you can see in the visible, you can see in the infrared, or you can see in the radio domain. So you can see here, this is exactly the same region of the sky, seen with different views. So in the visible, you see, this one we don't see anything here, because of the light, yeah. This is in the infrared, and this is in the X-ray. So in the X-ray, you see something totally different. You see when the stars are actually dying. To conclude, I think I hope I gave you a little flavor of the way we are doing data management. Insisting on the fact that for us, one of the challenges is the heterogeneity of the missions on the data sets, which probably is also something similar for you. You have heterogeneity of various sensors and devices. We need to ensure to maximize the science exploitation, and while ensuring at the same time the long-term preservations, which is not easy in an IT technology world which is changing radically every few years. Interoperability is very important, and I heard this message as well from you yesterday and today. So obviously this is very important to be able to interoperate the archives worldwide. On visualization of data, so one of our big tools is ESASky, and I can only recommend you to give it a try. Now the big change for us is toward this archive 2.0. Some people also use these terms of science exploitation platform. So it's not more an archive where you go and fetch data, download it to your place, and work at your place, but it's really a science exploitation platform which offers you access to data, access to metadata, user workspaces, disk space, and database spaces, but also an ecosystem where people can bring their own code and share their code with other scientists. And with this, I will leave it here, and I thank you all for your attention.